Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be expanding our knowledge of simple ionic compounds to much more advanced species involving both metals and polyatomic ions. So one of the first things that's really good to address is last time we were mostly working with alkali earth metals as our cations. However, there's a huge range of other cations you can use. Specifically, I like to focus in on the metals. So there's plenty of metals that only form a single ion. I'm mostly looking at things like zinc and silver. But there's also this wide range of transition metals from the middle part of the periodic table that can adopt multiple forms of ions. So this involves things like chromium, which can be 2 plus or 3 plus, iron, same thing, 2 plus, 3 plus, copper, plus 1 plus 2, and mercury can even do a monatomic or a diatomic metal cation, both with the same plus 2 charge, but this gives a different oxidation state. So as a result, in order to keep all of these various metal names straightforward, one of the first things we can do is simply just write the charge in Roman numeral behind the metal ion. So chromium 2 means I have a 2 plus oxidation state. Chromium 3 plus oxidation state. This is going to have a positive 3 charge. And using this, I can balance the rest of my ionic compound just like it was a simple ion, as long as I know what I'm dealing with. However, one of the things that you should watch out for is that some of these names are often, some of these metals are often referred to by their earlier names. So for example, iron's been around for a while. So iron 2 plus is often called ferrous iron. So this us means that I've got the lower charge, and if I've got ferric iron, this means I'm going to have the higher charge. So again, us means you're going to have the lower oxidation state. Ik means you're going to have the higher one. So for iron, this goes in between the 2 plus and the 3 plus. But one of those other metals we've been using for a long time has been copper. So copper 1 is now cuprous, and copper 2 is now cupric. Now, it is actually very useful because you're going to find plenty of compounds out in the world that are cuprous or cupric, or ferrous or ferric. For example, if you're working with ferric oxide, which is a form of rust, you're going to have different reactivity than ferrous oxide, which is a completely different oxidation product of iron, and will have very different chemical properties. So let's go ahead and see how these names are actually put into use. So let's go ahead and take a look at this copper 2 oxide. So if I have a copper 2 oxide, you can use that as the name, and that is just fine. However, don't be too surprised if you see cupric oxide. It's referring to the same compound. And again, similar procedures can hold for cuprous, ferric, ferrous. These are going to be the major ones that use this older naming scheme, but you will occasionally see it for other metallic ions. And again, if you do see this us, ik, us, lower oxidation state, ik, higher oxidation state, and you should be fine. Now let's go ahead and take a look at some of these polyatomic ions, because as we saw just a little bit for mercury, turns out a lot of ions may actually have multiple atoms in present in the ion, and this means that the charge is overall distributed. So one of the good examples here is the ammonium ion. You've probably seen plenty of ammonium compounds. And so you may have, say, ammonium sulfate. This is a common fertilizer. And it really kind of shows that once you have these various cation and anionic names, you can just insert the names of this overall ion into your general naming convention. So for example, you can do ammonium sulfate, common fertilizer. Ammonium phosphate is another very common fertilizer, though occasionally it occurs as ammonium hydrogen phosphate. So again, all you need to do, leave ammonium. If you're dealing with ammonium, you'll just use the name ammonium. If you're dealing with any of the anions, similarly enough, you'll just drop the ion and use the name. However, there is a fair number of ions out there that you should try and be familiar with. Again, ammonium and sulfate are two of the common ones. We've already been talking a little bit about nitrate. Hydroxide is the quintessential base, and everybody knows cyanide because it's poisonous. But again, I'll be trying to include a fair number of these into examples so you can kind of get familiar with all of the various common polyatomic ions. And again, one of the things I do like to emphasize is it turns out there are relatively few of these polyatomic cations. You can see we pretty much have ammonium, and if you want to count it, mercury. And that's kind of it for the polyatomic cations. However, there is a huge range of polyatomic anions. And this is partially because if you're going to be anionic, this means you're typically gathering electrons, which is very common for elements on the right side of the periodic table, those nonmetals, which tend to be very good at forming these molecular ions. Now, we're going to go ahead and go through a couple of these. So one subclass of these polyatomic ions are called oxoanions. And this is just a way of saying that I've got some sort of non-metal compound that's bound to a fair number of oxygens. And one of the cool things about a lot of these oxoanions is they can adopt many different forms depending on the different oxygens they have. You can see this, for example, with chlorine and iodine, and as well as things like bromine in between. Very common for the halogens, but we'll find a fair number of other compounds that do this as well. So what we do is we often assign one of these ions as kind of our default compound. So for example, with chlorine, it's chlorate. And whatever our default, we consider our default charge state is going to have this ate suffix. However, if it turns out that we're missing a single oxygen atom, so in this case, I go from O3 to O2, it's now chlorite. So we replace that ate with an ite. Then if it has an additional oxygen atom, so we go from O3 to O4, we're now per-ate. So in this case, it's perchlorate, but for iodine, it's per-iodate. So we start with iodate, and now it's per-iodate. Now, similarly, we can be down 2 oxygen atoms. So we go from iodate to iodite to now hypoiodite. Hypo essentially is saying that we don't have enough. Good way to think about this, think about hypothermia. Not enough heat, in this case, not enough oxygens. So again, iodate becomes hypoiodite and chlorate becomes hypochlorite. This one you might actually be familiar with because hypochlorite is the active form of bleach. So this is often found in bleach as sodium hypochlorite. So again, as the salt. And again, this really helps illustrate how useful many of these polyatomic ions are. So again, just a quick reminder, if we have very few oxygen atoms, we're going to start with hypo because I don't have enough. Then we go to ite, then ate. Then if we're totally saturated with oxygens, it's going to be per-ate. So whether that's perchlorate, perbromate, periodate, as well as a couple others that we'll see along the way. Now, these are some, these oxoanions just form a subclass of some of our polyatomic ions, but you'll notice that a fair number of them are represented here, including our chromates or dichromate if I have 2 chromate ions together, as well as other species like permanganate. And again, you'll notice they all follow these same nomenclature, but there's plenty of other ions out there. And in general, if you're not an oxoion, you're going to tend to have a suffix of "ide." So for example, cyanide or hydroxide. So these, if you see this "ide," usually means we don't have an oxygen, and we can go ahead and follow a lot of the same schemes we would with chloride or any other atomic ion. So again, cyanide and hydroxide are 2 very common ones. Now, one of the other things you should watch out for, and does actually show up on the list, is that we can take some of these oxoanions, like phosphate, and then it turns out in phosphate's case, we have a lot of negative charge. We have a 3- charge, which means that it's actually pretty good at attracting lone protons. So this can often make things called, combined with those hydrogen atoms, to make hydrated, make protonated ions. So in this case, we can have, adding 1 proton, hydrogen phosphate, and in 2 protons, it would be dihydrogen phosphate. And we again see very similar things with sulfite and sulfate, as well as, even though it's not on here, oh, actually here it is, phosphate and dihydrogen phosphate. All of these are very common in biological systems, as your blood actually pumps a lot of hydrogen phosphate and dihydrogen phosphate to help kind of manage the pH of your blood, which is a topic we'll be talking about much more next semester. So this idea of being able to combine larger molecular species is something we're going to tackle a lot more next time, as we're going to talk about molecular species, and as part of that, acids and bases. And turns out this is exactly what we're dealing with when we're looking at some of these ions. So until then, take care.